In this final video of topic 3, we're going to be looking at power series in a complex variable. This will extend some of the discussions we had in topic 2, and we'll also see the link between complex power series and analytic complex functions. As a quick recap of the previous video, we saw that the real and imaginary parts u and v that satisfy the Cauchy-Riemann conditions for a complex function are harmonic functions. In other words, they satisfy Laplace's equation. We also looked at complex functions as conformal mappings. And lastly, we looked at some terminology surrounding the analyticity of a complex function. After watching this final video, you should be able to find the radius of convergence for a complex power series using the ratio test. And you should also be able to expand complex functions using geometric series in a complex variable. And we will pursue such expansions later in topic 6. After finishing this video, I encourage you to have a go at the questions in problem sheet 3. There are plenty of examples to help test your understanding of all that we've covered in this topic. And with that, let's start this final video.
Let's look at power series in a complex variable, and we'll be looking at the link to analyticity. Consider an infinite series of complex numbers. Given by this power series. P of z is a constant term, a term in z, plus a term in z squared, etc. We write this as the sum from n equals 0 to infinity of complex coefficients Pn times z to the n. This is a complex power series centered about z equals 0. We saw in topic 2 how to investigate convergence for real series. How do we go about that for complex series? We ask the question, is this complex power series P of z absolutely convergent? In other words, the ordering of the terms doesn't affect the convergence. As before, we can apply the ratio test again. And the reason that the ratio test we earlier used for real series is valid here is that we are considering the sum from n equals 0 to infinity of the absolute value of Pn z to the n, which are real numbers, and so this is again a real power series. This looks at the limit as n tends to infinity of the n plus 1th term, which is Pn plus 1 times z to the n plus 1, divided by the nth term, which is Pn times z to the n, and we take the modulus of this complex number. We can take a factor of modulus z out of the front, and we're left with Pn plus 1 divided by Pn, taking the modulus. From the ratio test, we know that this has to be less than 1 for convergence. Therefore, the series converges if the modulus of z is less than the limit as n tends to infinity of, and then we flip the numerator and denominator because we've taken it to the other side. We define this quantity on the right hand side as r, which is the radius of convergence. And you can compare this to the interval of convergence on the real number line that we saw when dealing with real power series. we can say that if the modulus of z is less than r, then P of z is an absolutely convergent power series. If the modulus of z is greater than r, the complex power series diverges. And finally, if we're looking at complex numbers whose modulus equals the radius of convergence, then the ratio test is inconclusive. In the complex plane, this radius of convergence defines a circle. Where its radius is r. We note this is the circle of convergence. So values of z that fall within this circle give complex power series that converge. We've shown that this complex power series is absolutely convergent, which means we have that the sum of the absolute terms converges. Recall from topic 1 that we extended the triangle inequality to show that the sum of the absolute value of some collection of complex numbers labeled Wn upper bounds the absolute value of the sum of those complex numbers. This means that the modulus of the complex power series also converges. And so our complex power series, P of z, given by the sum of Pn, z to the n, converges for z less than the radius of convergence. We can look at a quick example of this. Let's consider the complex power series where all of the coefficients are 1. In other words, our power series is 1 plus z squared, and so on. If we apply the ratio test, we can find the radius of convergence. The limit as n tends to infinity of the nth over the n plus 1th term is simply 1, which is our radius of convergence. Therefore, this series converges for complex numbers whose modulus is less than 1. By the same technique used in our discussion of real geometric series, we can identify that this P of z is given by 1 divided by 1 minus z. This is done by similar arguments of absolute convergence. We have this power series expansion of 1 over 1 minus z. Hence we see that the complex function we can write as 1 over 1 minus z is analytic in the region modulus of z less than 1. In other words, it is single valued and it has a well-defined derivative as evidenced by its expansion as a complex power series. Each term in that power series itself has a well-defined derivative. Analyticity in a region pictorially means we can do something like this. we have a circle of convergence again, where it crosses the axis at 1, -1, I, and minus I. And we note there are no singularities in the circle of convergence. However, on the circumference of the circle of convergence, our function f of z is singular. Here. It fails to be analytic, and we will see the consequences of this later on in the course. In any case, we have that within the circle of convergence, we can write f of z as the sum of Pn, z to the n, where in this case all of the coefficients Pn are 1. All of these terms are analytic within the radius of convergence. That means that we can simply differentiate the left and right hand side to obtain the derivative of our function as another complex power series, where now the coefficients are given by n times Pn and then z to the n minus 1. Therefore, any power series can be differentiated any number of times within its circle of convergence. And in fact, in the problem sheet, you will prove that the differentiated power series has the same circle of convergence. A final important point that links this discussion of complex power series to our concept of analyticity is that locally convergent complex power series can be used to define an analytic complex function. We will return to this later in the course to discover how to construct Taylor series expansions for complex functions. And that's complex functions that are analytic. Complex functions expanded in a region where they fail to be analytic are described by another type of power series. As a final point, let's consider another famous power series. Let's consider 1 plus z plus z squared over 2 factorial plus z cubed over 3 factorial, and so on. The radius of convergence r is given by the limit as n tends to infinity of the nth coefficient divided by the n plus 1th coefficient. Substituting in, we have that this is 1 over n factorial divided by 1 over n plus 1 factorial, which is the limit as n tends to infinity of n plus 1, which of course approaches infinity. This means that the radius of convergence is infinite. Of course, you will have spotted that the power series that we've written here of this form is the expansion of the exponential function. This is analytic throughout the complex plane. and it is therefore an entire function. That's the end of this final video of topic 3. To quickly recap, we looked at power series in a complex variable and showed how to find the radius of convergence within which a complex power series converges. And we looked at a couple of quick examples before pointing out a connection with analytic complex functions. The ability to expand complex functions as power series in different regions of analyticity is a very important topic that we will be revisiting later in the course in topic 6. This is the end of topic 3. You can now have a go at the accompanying problem sheet to test your understanding of all the concepts that we've gone through in these videos. Thanks for listening. And next up is topic 4, where we're going to look at multi-valuedness of complex functions.